For most of human history, time and space were thought to be two completely separate things. Space was the stage. Time was the clock on the wall. Newton described space as a kind of absolute container, infinite, empty, unchanging, and time as something that ticked forward at the same rate for everyone, everywhere, always. You could move through space, but time just happened to you, universally, like weather. That picture is wrong. And the person who first showed us that was a 26-year-old working as a patent examiner in Bern, Switzerland, in 1905, who had been quietly thinking about what it would look like to ride alongside a beam of light. Albert Einstein's special theory of relativity didn't just update Newton. It dissolved the foundation. It said, space and time are not separate things. They are two dimensions of a single four-dimensional structure. And that structure responds to motion. Meaning, if you move faster through space, you move slower through time. The clock on your wall ticks differently depending on how fast you're traveling through the universe. That's not a poetic line from a motivational poster. Einstein meant it literally, and the physics backs him up in ways that are, once you sit with them, genuinely difficult to process without feeling something shift in you. Let's start with something small, because the small things are where reality gets strange first. GPS satellites orbit Earth at roughly 12,500 miles up, moving at about 8,700 miles per hour. They carry atomic clocks, incredibly precise instruments that measure time in billionths of a second. And those clocks, because of the satellite's speed and their distance from Earth's gravity, gain about 38 microseconds per day compared to clocks on the ground. That's not a lot, but it's enough. If engineers at NASA and the Air Force didn't account for that drift, if they didn't correct for the fact that time is literally running faster up there, your GPS would be off by about 7 miles a day. And within a couple of weeks, it would be completely useless. The technology in your pocket works because time is not universal. Your phone knows where you are because Einstein was right. That's not an abstraction. That's your Tuesday morning commute. But here's where it gets stranger. And this is the part one want to stay in for a while, because I think it's the part most people skip over too quickly. In 1908, Hermann Minkowski, Einstein's former mathematics professor, took what Einstein had described algebraically and gave it a geometric shape. He said, imagine space and time not as two different things, but as one unified four-dimensional continuum. Every point in that continuum has 3 spatial coordinates and 1 time coordinate. He called it spacetime. And then he said something that sounds almost too strange to accept. He said that events, not objects, not particles, but events, are the fundamental units of reality. Not the chair you're sitting in, but the event of you sitting there, at this particular place, at this particular moment in time. That event is a fixed point. It exists in space-time permanently. It does not go away when the moment ends. Every moment you have ever lived, every single one, still exists as a coordinate in space-time. The afternoon you learned to ride a bike. The night of your first heartbreak. The Tuesday morning you sat in traffic and felt, without quite knowing why, deeply, unexpectedly happy. Those moments are not gone. In the four-dimensional structure of space-time, they are still there, permanent, unchanging, as real as this moment. Physicists call this the block universe theory, or eternalism. And it's not a fringe idea. It's the interpretation of space-time that most closely follows directly from what the math says. I remember when I first really understood what that meant. I was rereading a passage from the physicist Sean Carroll, who's done some of the clearest writing on this in recent years, and he described it this way. Imagine you're looking at a map of the United States. Chicago and Los Angeles are both on the map at the same time. Neither is more real than the other. Neither comes before or after. They just occupy different coordinates. Now extend that logic to time. Yesterday and tomorrow are just different coordinates on a four-dimensional map. They both exist. You're just located at one point right now. The reason we feel time moving forward, the reason you experience this documentary in sequence, sentence by sentence, is not because time itself flows. It's because of entropy. Because the universe started in a state of extremely low disorder and has been expanding into higher and higher disorder ever since. The arrow of time isn't built into the structure of spacetime. It's a thermodynamic pattern. It's the direction in which complexity tends to unravel. Which means that the feeling you have of moving through time, of experiencing a past that recedes and a future that approaches, is something your brain constructs. A model, a narrative built by a nervous system that evolved to navigate a world of causes and consequences, not to perceive four-dimensional geometry. Now, you might be asking, okay, but isn't that just philosophy? Doesn't physics deal with things we can actually measure? And the answer is that Einstein didn't stop at special relativity. 11 years later, in 1916, he published the general theory, and that's where spacetime stopped being an abstract concept and became something physical. Something that has mass. Something that can move. General relativity says this: matter and energy don't just exist inside spacetime. They warp it. They curve it. A massive object, a star, a planet, a black hole, bends the geometry of spacetime around it. And what we call gravity is not a force, in the way Newton described it. Gravity is the curvature of spacetime. When the Earth orbits the Sun, it's not being pulled by an invisible string. It's following the straightest possible path through a spacetime that has been bent by the Sun's mass. There's a classic way of visualizing this. Imagine a rubber sheet pulled tight, and you place a bowling ball in the center. The sheet curves downward around the ball. Now roll a marble across the sheet. It curves toward the bowling ball, not because of a force, but because it's following the contour of the surface. That's gravity. That's spacetime. The geometry itself is the physics. And unlike Newton's gravity, which was instantaneous and mysterious, action at a distance, as he admitted was troubling, Einstein's gravity travels at the speed of light. It propagates as waves through spacetime, ripples in the fabric. Which brings us to one of the most astonishing moments in the history of physics. September 14th, 2015, 5:51 a.m. Eastern Time. At the LIGO Observatory in Livingston, Louisiana, and its twin facility in Hanford, Washington, a signal arrived. A specific kind of distortion, not in sound, not in light, but in the structure of spacetime itself. The distance between two mirrors, held 4 kilometers apart by one of the most stable laser systems ever built, changed by less than 1,000th the diameter of a proton. That change was a gravitational wave. It had originated 1.3 billion light-years away, from two black holes, each roughly 30 times the mass of the Sun, spiraling into each other and merging. In the final fraction of a second, they released more energy than all the stars in the observable universe combined. Not as light, not as heat, as a ripple in spacetime itself. And that ripple traveled for 1.3 billion years, longer than Earth has existed, longer than complex life has existed on this planet, crossed the entire observable universe, and arrived here, at Earth, and gently, almost imperceptibly, stretched and squeezed the geometry of space in Louisiana and Washington state, and instruments built by human hands detected it. When the LIGO team published their paper in early 2016, confirming the detection, confirming that spacetime itself vibrates, it was the first direct observation of something Einstein had predicted exactly 100 years before. And it was the first time humanity had, in any meaningful sense, heard the universe. General relativity, Einstein's description of spacetime, is one of the most accurate theories in the history of science. It has been tested and confirmed to extraordinary precision. But it breaks down. There are places where it stops working. Where the equations produce infinities, which in physics is a way of saying, our model has hit a wall. Those places are called singularities. And the most famous ones are at the center of black holes. Inside a black hole, past the event horizon, the point of no return, general relativity predicts that spacetime curves so severely that all paths, for any object, lead toward the center. You cannot stop falling. There is no direction that isn't toward the singularity. Space and time, in a very real sense, swap roles. The future is not in front of you. The future is below you. Time becomes a direction in space, and there is only one way to go. At the singularity itself, the curvature of spacetime becomes infinite. Which means the theory breaks. The math produces nonsense. And the reason it breaks is that general relativity doesn't account for quantum mechanics, the description of physics at the smallest scales. Where general relativity treats spacetime as a smooth, continuous surface, quantum mechanics suggests that at the smallest possible scales, the Planck scale, roughly 10 to the negative 35 meters, spacetime may not be smooth at all. The problem is that we don't have a theory of quantum gravity. We have two extraordinarily successful theories, general relativity for the very large, quantum mechanics for the very small, and they are fundamentally incompatible. They cannot both be exactly right. And somewhere in the gap between them is the true nature of spacetime. String theory, loop quantum gravity, causal set theory, emergent gravity. These are the frameworks physicists are working with right now, in 2026, as this is written, and none of them has yet produced a prediction that we can confirm with an experiment. The question of what spacetime really is, at its deepest level, remains genuinely open. Let me tell you something about the philosophy here, because I think it matters beyond the physics. For centuries, Western philosophy, and a lot of Eastern philosophy too, has struggled with the problem of impermanence. Things end. People leave. Moments vanish. The Stoics had a practice called memento mori, remember that you will die. Not as a morbid exercise, but as a way of paying attention. The Buddhist tradition builds its entire ethical framework around the recognition that clinging to permanence is the source of suffering. The Tao Te Ching opens with the observation that whatever can be named is already not the thing itself. And now physics, coming from the other direction entirely, from mathematics and telescopes and laser interferometers in Louisiana swamps, arrives at something strangely similar. Not that things don't matter, but that the way we experience time, as something that flows, that carries away what we love, may be a feature of our neurology, not of reality. If the block universe is correct, if every moment is a permanent coordinate in four-dimensional spacetime, then nothing is truly lost. The moment is still there, fixed, real, just located at a different address in the continuum. I'm not saying that makes grief easier. It doesn't, not immediately. But there's something quietly extraordinary about the idea that the universe doesn't discard its moments. That physics, in its own way, keeps everything. There's another layer to this I want to touch on, because it's one of the stranger implications of spacetime that doesn't get discussed enough. Simultaneity is relative. Two events that appear to happen at the same time from your perspective may not happen at the same time from another perspective. This isn't a matter of information delay, of light taking time to reach you. It's a fundamental feature of the geometry. Whether two events are simultaneous depends on how fast you're moving relative to the observer. Here's what that means in practice. Right now, this moment, as you're watching this, there are beings somewhere in the universe, hypothetically, for the sake of the physics, for whom the American Civil War hasn't happened yet. And there are beings for whom the year 3000 has already passed. Not because of time travel. Because simultaneity doesn't exist as an absolute fact. The universe doesn't have a single universal now. This is one of the things about spacetime that I think people hear, nod at politely, and then don't actually let land. The present moment, this specific sliver of now you're inhabiting, is not a universal feature of reality. It's a local one. Your now is yours. Mine is mine. And they are genuinely different coordinates on the same four-dimensional map. The philosopher Heraclitus said you can't step in the same river twice. He was being metaphorical. Physics is being literal. When the Event Horizon Telescope collaboration released the first image of a black hole in 2019, the supermassive object at the center of the galaxy M87, captured as a glowing ring of plasma against a dark shadow, and then followed it in 2022 with an image of Sagittarius A*, the black hole at the center of our own Milky Way, they weren't just taking a photograph. They were imaging the geometry of space-time itself. The dark region in the center of those images is not a hole in space. It's a region where space-time has curved so severely that no light can escape. The boundary of that shadow is the shape of the geometry. Near a black hole, time dilation becomes extreme. If you could hover just outside the event horizon, which would require an engine of almost unimaginable power, you would age enormously slowly relative to someone far away. Hours for you might be centuries for them. This is not fiction. It's the direct prediction of general relativity, confirmed indirectly by everything we know about the physics of extreme gravity. And if you crossed the event horizon, if you fell in, you might not notice immediately. There's no wall there, no visible boundary. You'd cross a point of no return and not feel it happen. But from that moment, the singularity is not ahead of you in space. It is ahead of you in time. There is no trajectory that avoids it. It is your future. Literally. What happens at the singularity itself? We don't know. The physics stops. The language of space-time breaks down. Whatever is there, it's something that requires a theory we haven't built yet. In space-time, every event, every point in the four-dimensional continuum, has what's called a light cone. Imagine an hourglass shape extending outward from any moment in time. The upper cone represents every event that could possibly be influenced by this moment, given that nothing travels faster than light. The lower cone represents every event that could possibly have influenced this moment. The space outside the cones, the parts of the universe that are neither in your past nor your future, is completely causally disconnected from you. Things happening there, right now, cannot reach you and you cannot reach them. They might as well be in a parallel universe, for all that the physics of causality is concerned. Your light cone is your universe. The slice of space-time you have access to, that has access to you. Everything else, everything outside those cones, is real, exists on the same four-dimensional map, and is permanently unreachable. There are stars out there, right now, burning and dying, and we will never know. There are events, extraordinary, universe-scale events, happening beyond the light cone that no human, no instrument, no signal we ever send will ever touch. The universe is not just large. It is permanently compartmentalized, cut into regions that can never communicate. Physicists use a phrase I love: the unreasonable effectiveness of mathematics. It was a phrase coined by the physicist Eugene Wigner in 1960, and it points at something genuinely mysterious. Why does mathematics, invented by humans, apparently as an abstract system, describe physical reality so accurately? Why does the geometry that Riemann developed in the 1850s as a pure mathematical exercise turn out to be exactly the language Einstein needed to describe spacetime 60 years later? Why does the universe seem to be mathematical at its core? Some physicists, Max Tegmark at MIT being the most prominent current voice, take this seriously enough to propose that the universe isn't just described by mathematics. It is mathematics. That physical reality and mathematical structure are the same thing. That spacetime isn't something that exists and then gets described by equations. Spacetime is the equations. I don't know if that's true, but I find it significant that the question can even be asked. That we have built minds capable of writing down symbols on paper that correspond, with extraordinary precision, to the geometry of the universe at cosmological scales. Whatever we are, evolutionary accidents, products of chemistry, brief arrangements of matter in a corner of a spiral galaxy, we somehow arrived at mathematics. And mathematics somehow arrived at spacetime. And that chain of coincidences is either the most astonishing thing imaginable, or evidence of something deep that we haven't named yet. Let me bring this back to something personal, because I think that's where this all lands. You are moving through space-time right now, not just through space, through time. Your body is aging. Your cells are dividing and dying. The light hitting your retinas is traveling at 186,000 miles per second, and the image you see is already a fraction of a moment old by the time your brain processes it. You are always living slightly in the past. You are always a step behind reality, constructing a model of the present from information that arrived a breath ago. And the version of you that existed an hour ago is a fixed coordinate in space-time. That version of you, wherever you were, whatever you were thinking, is permanent now. Crystallized, real in the four-dimensional sense. The universe remembers you even when you've forgotten yourself. I think it's actually one of the most quietly moving things that modern physics has to offer. Every moment of your life is permanent, not in any supernatural sense. In the most literal, geometric, physical sense. You leave a trail in space-time the way a ship leaves a wake in water. And unlike the wake, it doesn't fade. The question I keep coming back to, and I don't have an answer, and I'm not sure anyone does, is whether space-time is something the universe has, or something the universe is. Is space-time a container, the way Newton thought? A stage on which matter and energy perform? Or is it, as Einstein's work suggests, something more active, something that curves and bends and stretches and, as LIGO confirmed, vibrates? Is it a substance in its own right? And if it is a substance, if it has properties, if it can be disturbed, if it can carry waves, then what is it made of? Does that question even make sense? Can you ask what the most fundamental thing is made of without implying there's something more fundamental beneath it? The physicist John Wheeler, who coined the term black hole, spent the last decades of his career working on what he called the it-from-bit hypothesis. The idea that spacetime itself, and all of physical reality, might emerge from information. That the universe, at its deepest level, is not made of matter or energy or spacetime, but of something more abstract. Relationships, differences, information. We are made of atoms that were forged in stars. Every iron atom in your blood was produced in the core of a star that died before the sun was born. You are, in a completely literal sense, made of the universe looking at itself. Your existence, brief, uncertain, specific, is the universe developing something like a perspective. And you live inside space-time. Not on top of it, not alongside it, but inside it. Your past is written into its geometry. Your motion through it is governed by its curvature. When you feel the pull of gravity, you are feeling the shape of the continuum. When you age, you are moving through one of its 4 dimensions. When you dream, your brain is constructing a model of a reality that is itself a model of something stranger and deeper than any dream. The universe has been here for 13.8 billion years. The sun will burn for another 5 billion. The black holes at the centers of galaxies will outlast everything. Stars, planets, galaxies themselves, and slowly evaporate over timescales so long they make the current age of the universe look like a Tuesday afternoon. Against that backdrop, a human life is, by every measure of duration and scale, astonishingly small. A flicker, a breath, an event on the timeline that would be invisible at any meaningful distance. And yet, that flicker contains everything you have ever loved. Every meal that tasted exactly right, every song that arrived at the moment you needed it. Every conversation that changed something in you quietly, without announcement. Every night you drove home and the city looked like something you'd been given rather than something you'd earned. Physics doesn't make those things larger, but it puts them in their proper frame. And in the proper frame, a brief thing that is fully lived is not diminished by its brevity. It is clarified by it. The great unfinished question of space-time, whether it's continuous or discrete, whether it's fundamental or emergent, whether it contains everything or is contained by something we haven't named, will not be answered tonight. It may not be answered in our lifetimes. It may require a generation of physicists not yet born, using instruments not yet imagined, to find the thread that finally pulls the picture into focus. But I think there's something valuable in sitting with that incompleteness. In recognizing that the most honest thing physics can say about the universe, right now, in the spring of 2026, is, we have learned an extraordinary amount about the structure of reality, and we remain genuinely, humbly uncertain about its deepest nature. That uncertainty is not a failure. It's a frontier. And frontiers, by definition, are where the most interesting things happen. If you looked up at the night sky sometime recently, really looked, past the light pollution, past the habit of not looking, you may have felt something you couldn't quite name. Some version of the feeling I had in that Nevada parking lot. Something between awe and vertigo and a strange, unexpected gratitude. That feeling is not irrational. It's not sentimental. It's actually quite precise. You were sensing, in some non-verbal way, the scale of what contains you. You were feeling the edge of your light cone. The boundary of your causal universe. The quiet fact that the stars you were seeing were not where they are now, that their light left them years, decades, centuries ago, and traveled across the curvature of space-time to land on your retina in that particular moment. The universe is not indifferent to beauty. It just produces it on scales that require patience to see. And you, reading this, watching this, wherever you are, whatever you're carrying tonight, you are a coordinate in space-time. A real one, fixed, permanent. You were here. You thought about this. And whatever comes next, the universe, in whatever sense it keeps records, keeps that.